Hello, this is Daniel out of Bimpe, classmate of yours. Um, my lecture is on the kernel trick, um, which is sort of a product of support vector machines. This is a topic that I find certainly fascinating. I've used it before. I had a natural language processing project using Twitter data, and I ran a series of different models, support vectors being one of them, with the kernel trick and without. And I found that using the kernel trick, I was able to get a better accuracy score on my model. And once that happened, I was kind of just fascinated about this idea that you have this original data set, that you grab, from wherever. It has a certain dimensionality to it already, and you use a series of models to be able to try and separate the data linearly as we keep on trying to do. And this idea that you can take that data set, the original data set, and transform it into however high of a dimension that you'd like, and basically learn in that space and find an optimal hyperplane. Use a support vector machine. That is, use a support vector machine that can linearly separate the data, is just very very cool. And you notice I said that you can transform the data into higher dimensions. There's actually a caveat to that, in that um, you're not actually doing the computation for the transfer in that transformation, and that's why it's called kind of like a trick. And so let's just get into it. Um, let's just recall that um, that a large margin for support vector machines is better for us. It reduces overfitting, so you can generalize better to new data, and it gives you a bound on the out of sample error in terms of the number of support vectors. And again, just remember that support vector machines is basically an optimal hyperplane algorithm. Optimal meaning it maximizes this margin between the decision boundary, this black line, the separator, and the closest data points to each class, which are called support vectors. Those are these instances here. That's not quite a support vector, but that's because this is non-separable data. But just remember that the SVMs are optimal hyperplane algorithm, and it tries to maximize this margin, so that it can generalize very well. And so in the case where we have non-separable data, we can introduce these C parameters, which I think we've seen, or we will see, I guess, at the time of this recording. Is introduces the soft margin. So if you have these C parameters and you run the quadratic program with these new parameters, you end up with the soft margin that can tolerate misclassification. And so that introduces a trade-off where if you have a soft margin, you can generalize, you maybe can generalize better to new data, but that comes at the cost of incorrect classifications in some cases. And that's a trade-off we've already seen. So down here, these three charts are different methods to dealing with non-separable data. So we've already seen that we can transform our data. We can do nonlinear transformations on our data, and separate in that space. And so that's exactly what we're doing here with these two SVMs. We're using a second order polynomial transform You can see that everything's correctly classified. We have support vectors here, 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 and here. Even the third order correctly classifies. Even the margin looks even better. And again, you see the support vectors. This is, again, a third order polynomial transform, but this is used as regression. And this will probably, you can see the classifications are correct, but it's probably overfitting very much. You can't even see where the decision boundary like ends. So it'll probably generalize very poorly. And so, but this tells us something very interesting. We found an optimal hyperplane in a higher dimensional space. And you can see even in a higher, well, the third order is higher than the second, and you can see this one's even better. So it really begs the question, like, how high can we take them to get an even better support vector machine, or even better decision boundary? And also you can notice that these support vectors, there's not many of them, and the support vectors are the ones that dictate the decision boundary. And so if we had a theorem, which we do, that controls the out of sample error in terms of the number of support vectors, then we actually don't have to depend on the dimensionality at all of the feature space. So in other words, that means we can keep climbing to higher dimensions, and only use a few support vectors to create a decision boundary. So it's just a matter of the computational feasibility of reaching that high dimensional space, because remember that's comes at a cost. It becomes computationally infeasible to move to quite high dimensions. And those two things I mentioned are over here. This is the VC dimension theorem, which again tells us that basically the number of support vectors really doesn't depend on the dimensionality of the data set, which is important, as we'll see. So this is just a look back to our nonlinear transformation. So let's just remember quick that we have our original data set and our original dimensions. We transform the dimensions, and we separate the data into our new space, which we call Z space, and then we classify back down into X space. And so our hypothesis can basically ends up looking like this, or this over here, where we have we're taking basically the sign of the dot product of W tilde transpose with the transformation function of X. And remember, W tilde is just basically adding one more dimension to the highest dimension, or to our order polynomial. So remember, hyperplanes have to be at least one dimension more than our Z space, the dimensions in our V space. And so we have basically, we already know that one thing, that we can have a few amount of support vectors, or the number of support vectors can be bounded such that we can get a decision boundary in even a very, very high dimensional space. And so the question is can we use nonlinear transformations without actually physically transforming the data into Z space? Remember, transforming data is a computational constraint. Um, and so if the computational burden is lifted, or we can somehow get to that Z space without doing the computation, then we have the tools and we have the power to generate a separator in that space. And that's sort of like a magical thing, because you can then take your data set into infinite dimensions and find a separator. And so you have a much wider, I guess, space or ability to get a high accuracy on a model that was just um, trained in a low dimensional space. Um, and so that's the idea of the kernel trick. And before going into the math, I'll just explain the kernel trick on simple terms. So we define a kernel function um, that maps our training data into this high dimensional space where there's a separator that might exist. And then the kernel function computes the inner product between the input data in the high dimensional space and